Hello, my name is Fritz Tversky and I'm a research engineer working at the Solar Thermal Energy Department at CENER in Spain. Today I'm going to present the CAPTCHA project. The CAPTCHA project is about competitive solar power towers and has been financed by the European Commission in the H2020 project framework. First of all, the contents. I'm going to talk about the CAPTCHA project concept, then about the solar receiver, the regenerative system, and finally the prototype installed at the PSA. And I'm going to present some pictures of the prototype and some pictures of the operation itself. Okay. Let's start with the project concept. The project concept is about an innovative power plant concept where we try to introduce the combined cycle as power cycle. So we have a gas turbine as topping cycle and the Rankine cycle as bottoming cycle. And the second objective was to analyze a downsized heliostat, which is optimized for mass production, and also including a smart calibration concept in order to have the heliostat field well calibrated at all times. We have, regarding the power plant concept, we have here two key components. The first one is the solar receiver, and the second one is the regenerative system, which exchanges heat between the atmospheric airstream and the pressurized airstream from the power cycle. So the concept of the plant is the following. We heat atmospheric air to high temperatures up to about 1000 degrees Celsius. Then we charge a thermal energy storage system, and when we want to generate power, we divert the high temperature air to the power cycle, exchange heat with the regenerative system, and power the topping gas turbine. Okay. Next you can see here the two key components, the solar receiver and the regenerative system. Next we're going to talk about each of the key components by itself. We will start with the solar receiver. The solar receiver is composed of a ceramic matrix which is heated by solar radiation, and this ceramic matrix heats up the ambient air from ambient temperature to the objective outlet temperature, which is about 1000 degrees Celsius. And it's a so-called volumetric receiver where we observe the so-called volumetric effect, which states that the front surface temperature of the observer is lower than the exit temperature, in this way optimizing the thermal performance. The second key component is the CAPTCHA regenerative system, which is designed in order to exchange heat between two airstreams, between the atmospheric circuit and the pressurized circuit. And we have here two operating modes. One, in the first operating mode, we charge one regenerative bed, and in the second operating mode we discharge the regenerative bed in order to drive the gas turbine. Okay, and these two operating modes are interchanged sequentially and switched from one mode to another mode in order to obtain continuous power transfer to the gas turbine. Okay, this prototype is going to be has been installed at a research facility in the south of Spain, where an experimental tower was available. So we installed the key components in order to validate the concept in the relevant environment. Here we installed the solar receiver, which has a power of about 300 kilowatt thermal. It's quite small, about 1 square meter of aperture area, and Additional components were or have been the regenerative system in order to exchange heat between the atmospheric airstream and the compressed airstream. And then, of course, the third component in the tower is the gas turbine, which should produce electricity with the solar heat input. Okay. This prototype has been installed at PSA in the south of Spain, and here you can see a 3D picture of the prototype. I will start with the solar receiver here. The solar receiver you can see here in the background, looking towards the heliostat field. Then you can see here in the picture the atmospheric pipework with the atmospheric valves, which are quite big. The nominal diameter, the nominal internal diameter is about 150 millimeters in diameter, and the next thing you can see here is the pressurized piping, which has a diameter of about 50 millimeters. Okay, and the last component needed is the gas turbine. And the gas turbine is placed inside a frame where each component is fixed to the frame. And in operation mode, we heat air to high temperature in the solar receiver. Then we charge the regenerative system. And then once we want to generate power, we discharge the system in order to drive the gas turbine. Okay. In the next picture you can see, in the next slide you can see some pictures of the prototype installation. You can see here on the left hand side you can see the ceramic absorber modules, where each module has a dimension of about 14 centimeters of width, okay, and they're square shaped, and they are stacked on top of each other in order to form the final solar receiver. Then in the left bottom corner you can see the solar receiver casing transported to the installation site. Here we lift it and mount it to the nose structure of the tower, which is at this moment installed at the bottom level. And then once the receiver has been installed in this nose structure, we lifted up the whole thing to the tower, to the top level, okay? And there finally we mounted the solar receiver. You can see here on the bottom right corner a figure of the solar receiver. Here you can see some pictures of the internal view of the prototype. Here you can see the regenerative system, one regenerator, the other regenerator. Here is one turbine stage shown, and here you can see parts of the intercooler. And here in the background is the auxiliary air-water heat exchanger in order to divert the flow when we don't want to charge the regenerative system. Okay. You can see on the bottom right side the internal view of the solar receiver, and here the absorber cups, which were mounted inside the absorber in the receiver aperture area. Next, also the heliostat was installed at the PSA. This picture shows the heliostat developed within the Capture project, which has an aperture size of about 8 square meters, and it has smart components installed, such as the camera. Here you can see the camera installed on the heliostat, which is responsible for the smart calibration of the heliostat. With the help of the camera we can estimate the exact position of the heliostat, and once we know the position of the heliostat, we can readjust the position in order to optimize the aiming strategy. Okay. At the moment we are performing tracking experiments at the PSA, and the results are quite promising. Let's conclude the quite short introduction of the Capture project. Within the project we have installed a 300 kilowatt thermal prototype of a solar-driven gas turbine, and it's currently being operated in the south of Spain at the research facility PSA called Plataforma Solar de Almería. And we also made experiments with a downsized heliostat optimized for mass production, and the testing activity is currently ongoing. Thank you for your attention.